So this week we're going to focus on two concepts we talked about last week, work and kinetic energy, but we're going to try to see what the intimate connection between those two are this week. So we're actually going to start off by doing a few problems that you should be able to do based on last week's learning. And then I've designed these problems pretty carefully so that hopefully you notice some sort of connection at the end. So the Google Doc on Google Classroom has 3 problems for you to do. I'm going to show you a sample problem here. All right, so it says an 8 kilogram box has an initial velocity of 3 meters per second forward on a horizontal surface. For the next 4 seconds, the box is acted on by an applied force of 26 newtons forward and friction of 10 newtons backwards. A, how much kinetic energy did the box have at the beginning? B, calculate the work done by each force on the box over the 4-second span and calculate the net work done on the box. C, how much kinetic energy does the box have at the end? All right, so part A, I'll squeeze it in the top corner here. It's the most straightforward part. It says how much kinetic energy does the box have at the beginning. So I'm going to label that as K1 with a subscript of 1 standing for the beginning. And I'm simply going to apply the formula for kinetic energy, which is half mv squared. But I'm going to use V1 standing for the initial speed. So this can just be filled out. Half, the mass is 8.0, and the initial speed is 3.0. They give the initial velocity, so they give the direction as well, but you don't actually need the direction for the kinetic energy because it's a scalar. So I calculate all of that out. Half times 8 is 4. 3 squared is 9. So 4 times 9 is 36 joules. All right, so that's part A. Part B is going to involve more work. It says calculate the work done by each force on the box during the 4 seconds, and then calculate the net work done on the box. So net work is a new term, and you may guess what that means. It's simply the result when you add all of the individual works together that are done on the box. So we'll calculate the individual works first. So if I consider what are all the forces acting on this box, I think there's 4 of them. There's gravity and normal. And then there's applied force and friction. And it's asking us to calculate the work done by each of these forces on the box. Now, gravity and normal are simple. Actually, the work done by gravity is 0 joules because gravity is 90 degrees to the direction of motion of this box. And remember, if it's 90 degrees to the motion, the work done is 0. So the same thing applies for normal force. The work done by the normal force is also 0 joules because it's perpendicular to the motion of the box. However, for applied and for friction, it's not 0, so we have to calculate it. The formula for work is force times displacement times cosine of theta. So one thing we're actually going to have to calculate is the displacement. All right, so it's not given to us here. So let me do that first. So find displacement. All right, so for the displacement, using the kinematics formulas, I'm going to start with a list. My starting velocity is 3 meters per second forward. The time is 4 seconds. Okay, my goal is to find out V2. My goal is to find out displacement. So I'm going to need a third piece of information here, and that's actually going to be the acceleration, which I'm going to calculate using Newton's second law, net force divided by the mass. The net force here is simply the 26 newtons forward minus the 10 newtons backward. The applied force minus the friction is the net force. Divide that by the mass of 8. These numbers are nice. 26 minus 10 is 16. 16 divided by 8 is 2. So the acceleration is 2 meters per second squared forward. And that's going to let me get the displacement. I go back to my kinematics formulas, and it's the third one. Which is right here. By the way, I believe the formula sheet for this whole course is on Google Classroom in the general info section. So if you haven't already done so, you may want to print off the formula sheet, because we're in the third unit now. There's getting to be a lot of formulas. Hard to keep track of them all. Okay, I can fill in the values here. So 3 for V1, 4 for time, and then acceleration I just calculated to be 2, and then time squared would be 4 squared. Okay, so I calculate this out. 3 times 4 is 12. Half times 2 is 1. Times 4 squared is 16. So I've got 12 plus 16. That's 28. Okay, so having found the displacement, now I'm actually ready to find the work done by the applied force and the work done by friction. So the work done by the applied force will be the applied force times the displacement times cosine of the angle between the applied force and displacement. Well, the applied force is forwards, and the displacement is also forwards. They're in the exact same direction. So the theta is actually 0 degrees for the applied force. And what's cosine of 0 degrees? Cosine of 0 degrees is 1. So it will not really affect the equation here. So when I fill in the values, the applied force is 26. The displacement is 28 times 1. So it's just 26 times 28. I'll get a calculator out for that. That's 728 joules to 2 sig figs. Okay, so there's the work done by the applied force. And finally, I will do the work done by friction. So same idea, it's the force of friction, magnitude, times the displacement, magnitude, times cosine of the angle between friction and displacement. Well, this time friction is backwards, while the displacement is forwards. So they're in exact opposite directions to each other. That's a 180 degrees difference. So it's cosine of 180. And what's cosine of 180 degrees? Well, that's equal to -1. So this becomes force of friction is 10, displacement is 28, and cosine of 180 degrees is -1. So I multiply that together and I get -280 joules. So now I'm ready to get the net work. Okay, the net work stands for all of the works added together. So it's the work done by gravity plus the work done by normal plus the work done by the applied plus the work done by friction. So the two zeros for gravity and normal aren't going to play into this, but for the applied force, it's 728, and for friction, it's negative 280. So I put those together. And I get 448 joules. And that's the 2 sig figs. Okay, so that's part B. Now I'm going to do part C. Hopefully I can fit it in here. Actually, I'll shrink. Give myself some more room. Okay, part C. How much kinetic energy does the box have at the end? So in order to find the kinetic energy at the end, I'm going to need to know the ending speed, because kinetic energy is half mv squared. I'm going to need to know the ending speed. So I'll go back to kinematics again, actually. So find v2. So I'm using the three values I got here, and then I'm going to try to find v2. So that'll be the first kinematics formula that contains all those variables. Can rearrange that for v2. So that'll be multiply both sides by time to get acceleration times time, and then add v1 to both sides. Fill in the values. 2 for acceleration, 4 for time, plus 3 for v1. Okay, and that equals to 11.0 meters per second. So that's the speed I'm going to use when I calculate my final velocity, my final kinetic energy, which I'm going to call K2 for final. So it's half m v2 squared. It's half, the mass is 8, and I just calculated my final speed to be 11.0. Square that. All right, let's see. And I get 484. To 2 sig figs. Okay, so those are the answers to the three parts. However, the thing I want to show you, and I ask you to do this on the Google Doc, is there a relationship between these three answers? So there's a starting kinetic energy, 36 joules. And then the forces acting on it did a net of 448 joules on the object. And the final kinetic energy was 484. Well, what you might notice is that whatever the starting kinetic energy is, if you add the total work done on it, we actually equaled the ending kinetic energy. You can check that. We started with 36 joules of kinetic energy. If you add 448 joules to that, which was the net work, you actually get 484 joules. Okay, so this is what I mean by there's a connection between kinetic energy and net work. We're just starting to explore that in this lesson, and you'll do it for 3 more examples and try to see if that connection holds true. All right, and then we'll talk about that more in future lessons.